Welcome! In this session, we'll dive into problem number 527, word abbreviation. We'll explore the challenge of generating unique abbreviations for a list of words and discuss different approaches to solve it. Let's get started. In this problem, we are tasked with generating the minimum unique abbreviations for an array of words. An abbreviation for a word is created by taking the first character, the last character, and replacing the characters in between with the count of those replaced letters. However, if a word has 3 or fewer characters, it cannot be abbreviated. There's an important constraint: no 2 words in the input array can share the same abbreviation. If any abbreviations conflict, they must be expanded incrementally by adding more characters until each abbreviation is unique. The input is a list of lowercase English words, and the output should be a list of unique abbreviations corresponding to each word in the input array. Let's look at an example to understand this better. Given the input array of words, like God, internal, me, internet, interval, intention, face, and intrusion, the output is the unique abbreviations L2E, God, internal, me, I6T, interval, intend4N, face, and INTR4N. How do we arrive at this? The word like is abbreviated as L2E, where L is the first character, E is the last character, and 2 represents the number of characters replaced in the middle. Similarly, God and me are not abbreviated because their lengths are 3 or less. For words like internal, internet, interval, intention, and intrusion, their default abbreviation would have been I6T, but since these are not unique, we expand some of them incrementally to make each abbreviation distinguishable. For instance, internal is fully expanded to internal to avoid conflict with others. For the remaining conflicting words, internet retains the abbreviation I6T since no further expansion is needed for uniqueness. Interval is also fully expanded to interval, while intention becomes intend4N, and intrusion becomes INTR4N. This ensures that all abbreviations are unique. Additionally, face remains face without abbreviation since it is already unique as is. This process guarantees that every word in the input has a distinct representation in the output. Now consider another example where the input words are apple, apply, ape, and apples. Here, the output abbreviations are A3E, AP3Y, ape, and A4S. The word apple is abbreviated as A3E, and apply becomes AP3Y to ensure uniqueness. The word ape is not abbreviated because its length is 3 or less. Finally, apples is abbreviated as A4S. The constraints for this problem include having up to 400 words in the input, each with a length of up to 400 characters, while the total number of characters across all words does not exceed 10,000. Edge cases to consider include scenarios where all words are either too short to abbreviate, identical, or share similar prefixes and suffixes, requiring careful incremental expansion to maintain uniqueness. To solve the word abbreviation problem, we first consider the brute force approach. The intuition here is straightforward: for each word, we generate all possible abbreviations and then check which ones are unique. Since the first and last characters of each word are fixed, the number of possible abbreviations for a word of length n is 2 and 2. While this method is simple to understand and implement, it comes with significant drawbacks. Specifically, as the length of the word increases, the number of possible abbreviations grows exponentially. When you consider that this process must be repeated for each word in the list, the computational cost quickly becomes infeasible for large datasets. While the simplicity of this approach is a clear advantage, the inefficiency makes it unsuitable for practical use. Instead, we turn to an optimized approach that focuses on resolving conflicts efficiently. The core idea here is to progressively refine abbreviations by increasing their prefix lengths only when necessary, which minimizes redundant computation and ensures each abbreviation remains unique. The optimized approach can be broken down into a clear algorithm. First, we start by grouping words based on their initial abbreviations. For example, the word internal would initially be abbreviated as I6L. If conflicts arise within a group, meaning multiple words share the same abbreviation, we increment the prefix length for those words until their abbreviations become unique. Throughout this process, we keep track of the minimum prefix length needed for each word, ensuring we don't recompute unnecessarily. This method leverages the fact that conflicts tend to occur among words with similar prefixes and suffixes, allowing us to resolve these locally within groups. By iteratively increasing the prefix length, we avoid the inefficiency of enumerating all possible abbreviations up front. In terms of complexity, this approach is efficient. It operates in O, n*L, time, where n is the number of words and L is the average length of a word. This is because we refine abbreviations only for overlapping groups. Space complexity is linear, O, n, as we only need to store the abbreviations and the prefix lengths. The key insight here is that we compute only as much detail as necessary, which makes this approach scalable and efficient. An alternative method worth considering is the divide and conquer approach. In this strategy, we recursively split the list of words into smaller groups based on shared prefixes or suffixes. Each subgroup is processed independently to generate unique abbreviations, and the results are then merged to ensure no conflicts remain. This approach has a clear and structured design, making it easy to conceptualize. However, it comes with its own trade-offs. While effective at grouping and resolving conflicts, it introduces additional overhead in managing the recursion and merging results. This can lead to slightly higher space complexity, as each recursive call adds to the memory usage. Despite its elegance, the added complexity in implementation and resource management makes it less efficient for this problem compared to the iterative optimization approach. After evaluating the options, the iterative optimization approach stands out as the best strategy for this problem. It strikes the right balance between efficiency and simplicity, avoiding the exponential blowup of the brute force method while being more memory efficient than the divide and conquer alternative. By focusing on group-based refinement and progressively increasing prefix lengths only when conflicts occur, this approach minimizes unnecessary work. This makes it particularly well-suited for large datasets, where scalability is crucial. The iterative nature ensures that we handle conflicts efficiently, while the implementation remains straightforward compared to recursive methods. One trade-off of this approach is the need to carefully track prefix lengths to avoid redundant computations. Additionally, resolving conflicts may involve making multiple passes over the data. However, these drawbacks are minor compared to the significant gains in scalability and efficiency. Overall, the optimized iterative approach is the most practical and effective solution for tackling the word abbreviation problem. The problem we're tackling involves creating unique abbreviations for words while adhering to specific rules. The first and last characters of the word must remain fixed, while the characters in between can either stay as they are or be replaced by a count of how many characters are abbreviated. For example, the word apple could be abbreviated as A2E, where the 2 indicates that 2 characters, P and L, have been condensed into a count. This approach requires us to generate all possible abbreviations for the word while ensuring efficiency and avoiding duplicates. To achieve this, the key is understanding the fundamental rules of abbreviation, such as fixing the first and last characters and deciding for each internal character whether it should remain as a literal or be replaced with a count. For instance, some valid abbreviations for apple might include A4E, AP3, A3LO, or even the full word apple, depending on the choices made for the internal characters. Now, to quantify the total number of possible abbreviations, we note that each internal character has 2 states. It can either remain as is or be abbreviated. For a word with length n, there are n2 internal characters, which means there are 2 n2 combinations of these states. For the word apple, where n equals 5, this results in 2 5 to 2, or 8 possible abbreviations. To generate these abbreviations, one brute force approach is to use bitwise operations. Here, each internal character is represented as a binary bit, 0 for keeping the character literal and 1 for abbreviating it. By iterating through all binary numbers from 0 to 2 n2-1, we can systematically generate every possible pattern. For example, the binary representation 000 translates to the full word apple, while 101 maps to a 3e, where the first and third internal characters are abbreviated. Similarly, 010 corresponds to AP2e, where only the second internal character is abbreviated. This systematic approach ensures that every possible abbreviation is explored. To ensure the uniqueness of abbreviations, we use a hash set to store them as they are generated. The hash set allows us to check in constant time whether an abbreviation already exists, enabling us to skip duplicates efficiently. Once the generation process is complete, the hash set can be converted into a list to return the final collection of unique abbreviations. A key insight here is the simplicity gained by using binary representation for the abbreviation process. Each bit in the binary number directly maps to whether an internal character is kept literal or abbreviated. This eliminates the need for complex conditionals during generation. Additionally, the hash set plays a crucial role in maintaining uniqueness without requiring an extra nested loop for duplicate checks, making the process significantly more efficient. It's important to note the exponential nature of the problem. As the length of the word increases, the number of possible abbreviations grows exponentially, specifically as 2 and 2. For longer words, this growth can become computationally expensive, necessitating optimizations like generating abbreviations on the fly or limiting the number of results based on specific constraints. When implementing the algorithm, 2 primary data structures are used. First, the hash set ensures that all abbreviations are unique and allows for constant time lookups and insertions. Second, a list may optionally be used to return the final set of abbreviations in a specific order. Converting the hash set to a list has a linear time complexity, O(n), where n is the number of abbreviations stored in the hash set. Together, these data structures balance efficiency and functionality in the algorithm. Generating abbreviations involves a few key operations. Binary iteration is central to the process, where we iterate through all binary numbers from 0 to 2 n2-1. Each binary number represents a unique pattern of abbreviation based on its bits. For example, given the binary pattern 101 and the word apple, we traverse the word and construct the abbreviation by appending either a literal character or a count, depending on the binary bit. In this case, the result is A3E, where the internal characters at positions 1 and 3 are abbreviated. Duplicate checks are another critical operation. Before adding an abbreviation to the final list, we verify its uniqueness by checking the hash set. If the abbreviation already exists, we skip it, ensuring that the result only contains unique entries. These operations form the backbone of the algorithm, enabling efficient generation and storage of abbreviations. Finally, let's analyze the complexity of the algorithm. The time complexity is driven by the exponential growth of abbreviations. Generating all possible combinations takes 2 n2 time. Operations involving the hash set, such as insertions and lookups, are performed in constant time, 1, for each abbreviation. Thus, the total time complexity remains 2 n2. Space complexity is also 2 n2, because the hash set needs to store all unique abbreviations, and in some cases, a list is used to return the results. While this exponential growth is unavoidable due to the nature of the problem, these complexities represent an optimized approach to tackling it, leveraging efficient data structures and systematic generation techniques. Here, we start by importing the necessary module, defaultIct, which helps us group words efficiently. Inside the solution class, we define the words abbreviation method that takes a list of words as input. First, we initialize some variables, n to store the number of words, ans as a list to hold the final abbreviations, and prefix as a list of ones, where each element tracks the number of prefix characters fixed for each word. We also define groups as a defaultIct to group words by their initial abbreviation. Next, we loop through the words to generate their initial abbreviations using the helper method getAbbreviation. This method takes the word and the number of prefix characters to keep. The resulting abbreviations are used as keys in the group's dictionary, with the indices of the words sharing that abbreviation as the values. At this point, words with identical abbreviations are grouped together. The next step is to process these groups until all abbreviations are unique. This is handled in a while loop, where we start by creating a new groups dictionary to store updated groupings. For each abbreviation and its associated indices in groups, if only one word corresponds to an abbreviation, we assign that abbreviation directly to the corresponding index in ANS. For ambiguous abbreviations, we increment the prefix length for each conflicting word and recompute its abbreviation. These new abbreviations are then added to new groups for further processing. Here, the groups dictionary is updated to point to new groups, and the loop continues until all groups have been processed, ensuring that each word has a unique abbreviation. Finally, the method returns the ANS list containing the unique abbreviations for all the words. To handle the actual abbreviation logic, we have the getAbbreviation helper method. This method takes a word and the desired prefix length as inputs. It checks if the remaining length of the word, after accounting for the prefix and suffix, is small enough that abbreviation is not possible. If so, it simply returns the word itself. Otherwise, it constructs the abbreviation by concatenating the prefix, the count of omitted characters, and the last character of the word. This method ensures that abbreviations are constructed correctly based on the desired prefix length, balancing uniqueness and brevity. Here, we start by defining the word's abbreviation method, which takes a list of words and returns their abbreviations. First, we initialize variables to manage the computation. The result array will store the final abbreviations, and the prefix array tracks the number of characters fixed at the beginning of each word. Initially, every word has a prefix length of 1. Next, we create a groups map to group words by their initial abbreviations. Using a loop, we calculate the abbreviation for each word by calling the getAbbreviation method in group indices of words that share the same abbreviation. At this stage, words with identical abbreviations are grouped together, setting the groundwork for resolving conflicts and ensuring uniqueness. This setup lets us focus on processing ambiguous groups while preserving any unique abbreviations we find along the way. Now, we handle the groups of words with ambiguous abbreviations. If a group contains only one word, its abbreviation is unique, so we store it directly in the result array. For groups with multiple words, we increment the prefix length for each word in the group and compute a new abbreviation using the updated prefix length. These new abbreviations are then added to a new set of groups, which will be processed in the next iteration. This process repeats until all groups are resolved, and each word has a unique abbreviation. Finally, the getAbbreviation helper method handles the logic for generating abbreviations. If the abbreviation isn't feasible due to the word's length, the method returns the original word. Otherwise, it constructs the abbreviation by combining the prefix, the count of omitted characters, and the last character. This ensures that abbreviations are concise while maintaining uniqueness and clarity. To solve the word abbreviation problem, we start with the input list of words, like love, live, lick. First, we initialize some key variables. The number of words, denoted as n, is 4. We create an answer array ANS initialized with none values, 1 for each word. We also initialize a prefix array with all values set to 1, indicating the starting prefix length for each word. Additionally, we use a dictionary called groups to group words by their abbreviations. Initially, this dictionary is empty. Next, we calculate the abbreviations for each word using a prefix length of 1. For like, the abbreviation is L2E, where L is the prefix, 2 is the count of characters between the first and last letters, and E is the suffix. This abbreviation is added to the group's dictionary under the key L2E. Similarly, love and live also produce the abbreviation L2E, so they are grouped under the same key. Lastly, lick produces a unique abbreviation L2K, and it is grouped separately. At this stage, the groups are L2E, 0, 1, 2, L2K, 3. Now that the initial abbreviations have been generated, the next step is to resolve any ambiguities. For the group L2K, which contains only the word lick, the abbreviation is already unique, so we assign L2K to ANS, 3. However, the group L2E has 3 words, like, love, and live, which share the same abbreviation. To resolve this, we increase the prefix lengths for these words to 2 and recalculate their abbreviations. Like becomes Li1E, while love becomes Lo1E. However, live also recalculates to Li1E, which means there is still ambiguity between like and live. We update the group's dictionary accordingly, Li1E, 0, 2, Lo1E, 1, next. We address the group Lo1E, which now contains only love. Since this abbreviation is unique, we assign Lo1E to ANS, 1. For the group Li1E, which still contains like and live, we increase their prefix lengths to 3 and recalculate their abbreviations. Like becomes lick1E, and live becomes live1E, both of which are now unique. Finally, we assign lick1E to ANS, 0, and live1E to ANS, 2. The final answer for this example is lick1E, Lo1E, live1E, L2K. For the next example, the input list is apple, apply, ape. As before, we initialize the variables. There are 3 words, so n is set to 3. The answer array ANS is initialized to none, 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 and the prefix lengths are set to 1, 1, 1. the group's dictionary starts empty. Using a prefix length of 1, we calculate the abbreviations. For Apple, the abbreviation is A3E, which is added to the group's dictionary under the key A3E. Similarly, apply becomes A3Y and is grouped separately. For ape, no abbreviation is possible since its length is less than or equal to 3, so the word itself is used as its abbreviation and added to the group's dictionary under the key ape. At this stage, the groups are A3E 0, A3Y 1, ape 2. In this example, the groups already have unique abbreviations. The group A3E contains only Apple, so we assign A3E to ANS 0. Similarly, A3Y corresponds to apply, so we assign it to ANS 1. Finally, ape directly maps to itself, so we assign ape to ANS 2. The final answer for this example is A3E, A3Y, ape. Moving on to the next example, the input list is dog, cat, bat. We initialize the variables. There are 3 words, so n is set to 3. The answer array is initialized to none, 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 and the prefix lengths are set to 1, 1, 1. The group's dictionary starts empty. Using a prefix length of 1, we calculate the abbreviations. For dog, no abbreviation is possible because its length is less than or equal to 3, so the word itself is used as its abbreviation and added to groups under the key dog. The same logic applies to cat and bat, which are added to groups under their respective keys. At this stage, the groups are dog 0, cat 1, bat 2. In this example, all the groups already have unique abbreviations. The group dog contains only dog, so we assign dog to ANS 0. Similarly, cat corresponds to itself, so we assign it to ANS 1. Finally, bat directly maps to itself, so we assign bat to ANS 2. The final answer for this example is dog, cat, bat. The time complexity of the word's abbreviation function can be understood by breaking it into 2 main steps. First, we perform the initial grouping of words based on their abbreviated forms. For each word, the getAbbreviation function calculates an abbreviation using a prefix length of 1. Since this function operates in O, L, time for a word of length L, and there are n words to process, the time complexity for this initial grouping step is O, n asterisk L. This gives us an efficient starting point for handling the words, but more work is required to ensure uniqueness. Now, to ensure all abbreviations are unique, we use an iterative conflict resolution process. For groups of words with conflicting abbreviations, the prefix length is incremented by 1, and new abbreviations are calculated in O, L, time per word. These words are then regrouped based on their updated abbreviations. In the worst-case scenario, a word's prefix length may need to grow until it equals the word's full length, requiring up to L iterations for a single word. Combining this with the O, L, time per iteration, the worst-case complexity for resolving conflicts becomes O, n asterisk L squared. Adding this to the initial grouping step, the total worst-case time complexity of the function is O, n asterisk L squared. However, in practical scenarios, prefix lengths grow more gradually, making the average case closer to O, n asterisk L. The space complexity of the solution involves several components. First, the output array ANS stores the final abbreviations for all n words, requiring O, n, space. We also maintain auxiliary data structures, such as the prefix array, which tracks the prefix lengths for each word, and the groups in new_groups dictionaries, which map abbreviations to lists of word indices. In the worst case, where each word has a unique abbreviation, these dictionaries require O, n, space. Additionally, the getAbbreviation function uses temporary space for string operations, requiring O, L, space per word during computation. Combining these, the total space complexity is O, n plus L. Since n is usually much larger than L, the overall space usage is dominated by O, n. Let's compare this optimized approach to the brute force method. A naive solution would involve repeatedly comparing each word with every other word to check for conflicts, generating abbreviations until all are unique. This approach has a time complexity of O, n squared asterisk L, as each word would require comparisons against all other words. In contrast, the optimized solution uses hashing, specifically the group's dictionary, to group words efficiently and avoid redundant comparisons. This reduces the worst-case time complexity to O, n asterisk L squared. The space complexity, dominated by the group's dictionary and the result array, remains O, n plus L. When analyzing the best, average, and worst cases, we find that in the best case, all words already have unique abbreviations, resulting in O, n asterisk L. In the average case, prefix lengths grow moderately, and conflicts are resolved efficiently, keeping the complexity closer to O, n asterisk L. The worst case occurs when all words have highly similar prefixes, requiring L iterations to resolve conflicts, leading to O, n asterisk L squared. When solving the word abbreviation problem, there are a few common pitfalls to watch out for. First, overlooking edge cases can lead to incorrect results. For example, short strings like a or ab, or strings with repeated characters like AAA, are often mishandled. This can either cause the solution to crash or produce incomplete abbreviations. To address this, make sure to test your solution thoroughly with these edge cases. Next, failing to optimize for large inputs is another issue. Using a brute force approach to generate all possible abbreviations for long strings can quickly lead to exponential time complexity. For instance, a string of length 20 would generate over 260,000 abbreviations, which is computationally expensive. To avoid this, you can use techniques like memoization or pruning to eliminate unnecessary computations. Another common mistake is misunderstanding how uniqueness is defined. Some assume that abbreviations must be unique across all words globally, rather than within a given word set. This misinterpretation can lead to incorrect logic in your solution. Carefully reading the problem's constraints and clarifying the scope of uniqueness is essential to avoid this error. Another frequent mistake involves generating invalid abbreviations. For example, producing something like a 1B for the word ABC means you've skipped characters incorrectly, resulting in an output that doesn't match the expected format. To ensure correctness, it's important to use a systematic approach. Recursion and bitmasking are great tools for generating valid abbreviations while maintaining structure. Additionally, ignoring space complexity can lead to inefficiencies. Storing all abbreviations explicitly in memory, especially for large datasets, can quickly consume resources and even cause crashes. Instead, consider streaming techniques or generating abbreviations dynamically as needed to manage memory effectively. These strategies not only improve the performance of your solution but also make it scalable for larger inputs. In an interview setting, this problem is often used to evaluate your ability to recognize patterns and apply efficient techniques like recursion, bitmasking, or dynamic programming. Interviewers are typically looking for solutions that go beyond brute force approaches. It's also crucial to demonstrate your understanding of time and space trade-offs. For example, you should be able to explain how your solution avoids redundant computations. Don't forget to explicitly discuss edge cases, as this highlights your thoroughness and problem-solving skills. If the input size is large, consider strategies to reduce the search space using memoization or additional constraints. It's a great way to show optimization. Clear communication is key during the interview, so walk through your logic step by step, making sure to emphasize how you ensure the uniqueness of abbreviations. For additional practice, you might explore related problems like unique word abbreviation, which focuses on ensuring abbreviations are unique within a dictionary, or generalized abbreviation, which involves generating all possible abbreviations for a word. These problems can help you deepen your understanding of similar concepts. There are several alternative approaches to solving the word abbreviation problem, each with its own trade-offs. The brute force method is simple to implement, making it a good choice for small input sizes. However, it becomes computationally expensive as the word length increases, so it's not suitable for larger datasets. Bitmasking, on the other hand, allows for efficient generation of all possible abbreviations. While it requires careful implementation to ensure correctness, it's a powerful tool for optimizing abbreviation generation. Another approach involves using a tree for validation, which is particularly effective when working with multiple words and ensuring global uniqueness across a dictionary. The downside is the added space complexity, which may not be ideal for memory-constrained environments. Finally, dynamic programming can be used to reduce redundant computations, especially in scenarios where the problem involves overlapping subproblems, such as dynamically counting abbreviations. However, this approach may require significant pre-processing. Choosing the right method depends on the problem constraints and the trade-offs you're willing to make between time and space efficiency. Great job! To recap, we explored the problem of generating unique word abbreviations and discussed the brute force approach. Remember to practice similar problems to solidify your understanding. Thanks for watching, and don't forget to subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!